Okay, hello everybody, and now for some completely different. We have news on colliding hashes. The ball is rolling. One of the biggest challenges in the practical cryptography, finding a collision for secure hash, what is it? Don't know, is tackled. Learn how you can contribute. This event is given by Christian Richberger. He learned about practical results of the study and exploration, and he is from Graz. Please give him a big hand.
Yeah. Hello everyone, thanks for the nice introduction. And I will start right away with a question. Who of you guys have used a hash function today? Hands up. A hash function. Did you use a hash function today? Well, quite a bunch, indeed. Let's take a look at this list. Did you use an SSL secured website? Did you use SSH? Did you enter a password somewhere? Probably did you digitally sign something? Did you rely on integrity checks wherever? What all these things and many more have in common is that they rely on some properties, some security of a fundamental building block, hash functions. So let me ask you again, who of you used a hash function today? Very good. Well, there are several properties we want to have from these fundamental building blocks. Think of it as a pyramid, where at the foundation we have these fundamental building blocks, hash functions, ciphers, similar things. On top of that we have protocols and then applications. And of course we want our fundament to be as good and as strong as possible. So, hash functions. Of course they should be efficient and easy to compute. If they would be difficult to compute, nobody would want to use them unless in some niche areas. And there are two more properties we would like to have. I will go into them immediately. One of the properties is one-way, and the other one is collision resistance. The one-way property of a hash function. Well, this is our hash function. It accepts inputs of arbitrary length, outputs something of fixed length. It's called hash value, digest, fingerprint, whatever. And now it should be difficult to invert this hash function. It should be difficult to go back. Given a hash value, it should be computationally infeasible to find an input such that fed into the hash function results into this output given. Many applications rely on this difficulty. For example, if a hash function is used to store a password, we don't want to have an algorithm which allows to somehow reconstruct the password given the hash of it. Or the payment schemes like Hashcash relies on this one-way property, or the key derivation, which is commonly used if you have some sort of master key, derive some more key material from that. You don't want the case that once one of your subkeys is compromised that someone can go back to your master key. That's why this one-way property is very important. Many more applications. There's a second very important property, which is collision resistance. That's what I'm mainly focusing in the next 30-40 minutes or so. Think of calling this hash function twice. Of course, if you feed in the same input twice, you will also get the same output. It's deterministic. However, if you change something at input, something completely different should pop out at the end. What collision resistance means is that it should be infeasible to somehow find two different inputs that map to the same output. Well, the trouble is, as soon as the number of possible inputs is larger than the number of possible outputs, you can't prevent the very existence of collisions. But it shouldn't be easier than just randomly trying and hoping that you find a colliding message. I have an application, so well, collisions shouldn't happen. you need this property in integrity checks where you face adversaries. You need this when you use it for authentication in digital signatures in Macs. And it's also very often required by law, at least in Europe. Once your hash function is not collision resistant anymore, you shouldn't use this. As an example, digital signatures. If it would be possible to create two inputs to a hash function, for example, a contract, which map to the same hash value, where something like the sum is changed as depicted here, then this would also result into the same signature. And if you can do this in advance, if you can prepare these two versions, then actually can forge signature, and that's very bad, of course. Hash functions are a rather hot topic at the moment. The reason is that some new results shattered some doubts on the security of very commonly used hash functions. One of the interesting properties is that, as you noticed before, even though cryptography is very often about secret private keys, we don't have a key in hash functions. We still require some security, whatever that exactly means. The most important and most heavily used hash functions nowadays are SHA-1, which I'm now talking about, and MD5, an older one. What you see here is that they are all actually based on the same design strategy, namely on MD4, which was pioneered by Ronald West, the RFRSA, in the late 80s, early 90s. Well, what happened not that long afterwards, it was a very fast hash function, targeted for commodity processors, 32 bits. In 96, what happened, the German cryptographer Hans Dobertin found a very good attack on this hash function. He managed to come up with a colliding pair of messages for this hash function. Well, by then, Rivest already proposed a successor, MD5, and what also happened in the States, NSA, the American NSA also used this same idea and proposed their own hash function, their own family of hash functions to be used in their federal standards. It was called SHA, Secure Hash Algorithm. Not that long afterwards, they tweaked it a little and renamed it to SHA-1. And that was about in 95, and since then, this very hash function ended up in many, many standards. All of the RFCs are full of requiring SHA-1, many more. There's also an Australian variant of MD4 and an European variant of MD4. Everything fine until about 3 years ago. Suddenly a group of Chinese researchers came up with a rather new method and buff. Collisions for MD5, collisions for Haval, collisions for RIPE-MD. That was rather surprising at the time. And so for all of these hash functions, collisions have been produced. Around the same time, also the predecessor of SHA-1, SHA, was affected as well. The first theoretical hints that there might be weaknesses were already discovered in 98 or so, but it took 7 or 8 years until the first colliding message pair was produced for SHA. So there's not that much left, as you see. What about SHA-1? So far there's no colliding message pair, and there's a lot of uncertainty on if and how much is going to happen there. And you will learn about that soon. First of all, I would like to introduce you to this family and briefly outline how they look like and how they work. They are iterative in the sense that they accept always inputs of fixed length, operate on them, update an internal state, and produce some output which is either the output of the hash or fed in into a new round of inputs and processing and outputs. This goes on and on until the end of the input is reached and the final hash value is computed. This, what we call compression function, is divided into two parts: the message expansion and a state update. First, let's take a look at the message expansion. So we have 16 input words of 32 bit each, meaning 512 bits. They are expanded. In the case of MD4, MD5, and RIPE-MD, this message expansion is a very simple process, very fast, of course. It's about copying message words and shuffling them around a bit, not more. The NSA designs, SHA and SHA-1, they do a little different things. In fact, they use a linear recurrence relation to derive the expanded message words, which is supposed to make things more complicated. Then the newer members of the SHA family, there's even more complicated stuff going on. Here there's a non-linear recurrence relation. What you see in general, this tendency of increased design complexity. Of course, these changes make them slower, which is not that nice. It supposedly makes them more secure, but what the problem is, because it's more complex, it's also harder to analyze, and it's less likely to be certain about the security. Okay, that's the message expansion. Let's take a look at the second part, the state update. Again, what we see is an increase in design complexity. MD4 was very simple, 4 state variables, very simple building blocks. In the case of SHA, we have already 5. In the case of SHA-2, 8. The building blocks are simple operations meant to be very fast on commodity processors, model addition, XOR, bit shifts, simple Boolean functions. Again, they are more complex, makes them harder to analyze, so supposedly more secure. How would we want now to try to produce a collision? Well, think of the picture I had before. We call the hash function twice, different inputs, and somehow try to find an input that maps to the same output. Well, we can try to start with one input and only flip 1 or 2 bits, a very small number of bits, such that hopefully differences won't spread too much, and in the end difference will cancel out. So our goal is to find a difference between 2 messages, such that in the end, after processing, the difference disappears. And hence we have a collision. Well, to get a feeling for that, let's do the most simple case. We flip just a single bit and let's see what happens. So we zoom in, flip a bit here, the first message word. Zoom in again. So we flip a bit here. Not much happens, it's only copied to this particular state variable. So this one is affected now. Well, in the second step, variable A is copied to B. Variable A is also rotated by 5. Changed here, copied to A again. So in the next step, already 2 of the 5 variables are affected. While this goes on, A is copied to B again in the next step. B is rotated, copied to C. B also goes into this function F, does something, and again influences the new variable A. So as we see differences spread, it doesn't seem to be a lot of control possibilities. Goes on. Guess you get the idea. And if you now take the bird's eyes view again, what we did, we flipped a single bit here, which caused a number of bit flips at the output of this message expansion, and in turn caused some bit flips at the beginning of this state. But what happens rather soon in the course of, in the case of SHA-1 it's 80 steps, rather soon in the course of these 80 steps, differences spread uncontrollably, randomly, and what we would want is that in the end we don't have differences anymore. We would want to get rid of all these red dots. That's actually how a good hash function is supposed to work. No way to control how differences spread. Well, after lots of head scratching, what happens is that if you don't flip a single bit, but a certain set of bits, not that many, maybe 20 or so, first of all you have a particular pattern at the output here. What happens is that there is a small chance that the sequence of differences throughout this state here looks like that. As you see, a lot less red dots. In the beginning, a huge mess, actually quite complex to figure out what's going on there and what is supposed to go on there. But if something like that is possible, hash function is not good. That's what is called a differential attack. So the idea is to have a message, try the same message with just some bits flipped, and hope that you observe this particular sequence of differences throughout the state. If that happens, then you are already on track towards a collision. Well, as you saw, there were still some red dots at the end. So that's actually not a collision, but what you can do is to just have a second block. So that's the picture of before. The first block, we have a small number of red dots in the end. It's not a collision, but it's a near collision. The hash value is only differ in a few bits. But what you can do now is to have a second block, the same message difference. In the beginning, a little different sequence of differences, but then the same sequence. What you end up with is exactly the same pattern of red dots in the second block. And you can hope that, because of this feed-forward operation here, you can hope that those differences cancel out. Near collision cancels the other near collision. Both you can have a collision. And these are all rather theoretical ideas and concepts. There are lots of technical hurdles on how to do this. And in fact, until now it was not clear at all how to really do it. The computational complexities to find a pair such that you have this funny behavior that not that many differences are in the state and differences are prevented to spread is also rather high. What I'm here now doing is to announce that we actually started to do this just this week. So we did a lot of head scratching, we designed this attack, the difference we need, and we also optimized the method to look for this colliding pair of messages. So let me ask you who has heard of BOINC? A few guys? Right. Who has heard of SETI at home or folding at home, these projects? Yes, some more. SETI at home is using BOINC. That's a distributed computing framework developed by some guys at Berkeley. So we are using this framework and send out work packages. You can think of this whole project as having 5 phases. The first 2 are more or less done. We finished to optimize the method to look for this SHA-1 collision for the first time. And now what we have is a huge workload we want to distribute. So you're invited to take a look and download this client. You can run it as a screensaver. However, there are lots of possibilities. However, that's a phase in the middle. Remember, we had this 2-block approach, which is kind of optimal, we found. Somewhere in the middle of the project, which will take several months, we will go ahead and design a new attack for the second block. And only then we can actually finish the search with a new distributed computing project, which is also looking for the second block, such that in the end, both near collisions we find here and here are expected to cancel out. Again, this will take lots of contributors and quite some time. In order to give you an idea on the difficulties people are facing, actually people are working on this already for several years, several research groups all around the world, and now the aim is to put an end on that. Several aspects which influence the method. First of all, the choice of message difference. That's the first thing. But then the choice of the sequence of differences to follow is very non-trivial. This all interacts with the speedup method chosen. The way bits are flipped such that the search space is covered very efficiently. And last but not least, which is somewhat different to older hash functions like MD5, is that there's an issue with the degrees of freedom available. Means we can design an attack. However, if you don't have enough degrees of freedom to really search long enough, then even if the attack is good, you will never find a collision. And these things all interact and influence, in the end, the work factor. It's only recently that we got an understanding of how all these things interact. Now we put them to work. Well, let me conclude. Stop using MD5. There's absolutely no reason to use MD5 in new designs. A guy from Microsoft told me that alone in Windows, and Windows alone, there are several hundreds of places in the code where MD5 is used in code. So there's certainly quite some effort to be done to look at all of those and see where the problem is. So far, no one could show a collision for SHA-1. It's a rather big challenge because it doesn't happen that often that a very widely deployed cryptographic algorithm like this hash function, which is standardized everywhere, can actually be practically broken. And the nice thing is, you can be part of it. Just visit this website, download the client, and help crunching. Well, with that I conclude. Thanks for your attention. I guess we have time for questions. Please.
Just a short question. You were talking about SHA-1. How about the probability of collisions for the other SHA hashes you had at the bottom of your picture?
Well, they seem to be designed with similar attacks in mind. Means they are more resistant because of their design complexity I showed you. But the thing is, most of the new techniques we developed, we haven't applied yet to SHA-2. So it might well be that we make some progress there as well, but that's work to be done, we don't know.
For the moment they are
Yes,
safe.
For the moment they're safe.
Hello.
Hello?
Can you elaborate on how you find a collision from two near collisions?
Sure. Shall I go back to the slide? Okay. So near collision, that's the first block. We look for a long time and find a message pair that only has, in this case, 2 or 3 bits that are different at the output. These differences are now copied to the input of the next block. And this makes the attack different, and hence a new phase is needed to design a new attack for this phase. But if you manage to incorporate these additional differences, which you don't have at the bottom because you start with 0, if you manage to incorporate them and still follow the same sequence of differences afterwards, and still manage to have the same difference at the output here, then what happens is that you always have this feed-forward operation, that meaning the differences here go here and are added. That's a model addition here, actually. And after then, there's a chance that these differences cancel out via this model addition operation.
So you don't actually need them to be near collisions. They just have to be the same,
Well,
different.
it doesn't help if they are completely independent, these near collisions. So if we have a particular near collision here, we need a matching near collision at the second block. Only then those cancel out. Yeah.
And you're looking for near collisions because they're easier to find?
Exactly.
Okay. Thanks.
In theory, it would also be possible to look for a sequence of differences that already collide here. But it turns out, after a lot of head scratching, that that cannot be more efficient than such a two-block approach. That's why we are doing that.
Thanks a lot.
I was wondering, at Boink, will you have both x86 and AMD 64 support on your clients for both
Well,
Windows
so
and
far
Linux?
we have binaries for Windows and Linux, but only for 32-bit platforms.
Okay,
But we will continue to support more platforms.
okay, I'll join that.
Right, great.
These attacks attack the message suspension, but is it possible to attack the message compression part also?
Well, actually, the attack work on both. It's expansion and compression. Only we work with the interaction of both building blocks. So the message expansion is an important part here. We use some properties in the attack, but we also use the fact that the compression has a certain structure.
So actually the major thing that we use hashes for and that we worry about for collisions is message authentication. So why exactly are we still bothering with MD4 derived algorithms when there's modern things like I think UMAC is provably unconditionally secure and as long as AES is secure? So
That's a very good point.
Do you have anything to say about other approaches?
Well, the thing is, hash-based Macs were very popular in middle 90s because fast hash functions were around. They were much faster than the available block ciphers. Yes, the block cipher back then was optimized for hardware. On your 32-bit machine, it was rather slow. That's why hash-based Macs turned out to be very, very popular. They went into internet standard. That's why they are still rather important. But indeed, there's other technology available based on block ciphers, which is now state of the art.
What options do we have if char is actually broken? Are there other hash functions you would recommend, like Tiger 192, or do they have the same problem?
Well, the area of hash function design and analysis is a very active one. In particular, in the case of Tiger, no one looked at it for quite some time, but since 2 or 3 years, people started to look at it, and indeed also there weaknesses were found. The other alternatives, like Whirlpool, which are already around for quite some time, seems to be very robust and conservatively designed. However, the organization which standardized this SHAs, SHA-1, also the SHA-2 family, is planning to create a new standard, which means this will be a multi-year effort to ask the research community for proposals. They will be evaluated similar to the AES process, and in the end, in maybe 4 years or so, a new hash function will be proposed and standardized based on all the insights we gained so far.
Is the combination of two hash functions still secure if both hash functions are insecure?
Well, you don't gain a lot. It's a little fail-safe practice. But if you want to be kind of efficient, that's probably not the best way to go.
Over the last year, much effort was put into the development of efficient implementations of hash functions based on block ciphers. Are these more secure constructs because they can rely on the research done on block ciphers?
So that's a very good point. indeed, people are thinking in that direction and try to build block cipher-based hash functions. Well, in a sense, it's harder to distinguish because you can also think of this building block as a block cipher. Not a very good one, but it's also a block cipher. And indeed, the design strategies used for the AES, for example, the standardized block cipher, can be also used in hash function designs. There are two proposals at the moment. One is Wellpro, the other one is Grendar, which use building blocks of the AES to make a secure and efficient hash function. But since in hash function you don't have a key, things are a little different. So it's not that straightforward to just use a good block cipher and make a hash function out of it. There's a little more to it.
Any more questions?
Okay. Thanks, everyone.